we will now take about 2-3 examples and just understand the concepts that so far we have covered in the course. So here you can see there is a 3-level neutral point clamp converter, and at a certain time the devices S3 and D6, okay, these two devices are conducting. So which among the following conditions for the output voltage VAO, okay, VAO and current I is true? Okay, so in this case, this device S3 and D6 are conducting. So which means that this current will be flowing like this. Okay, there is no other possibility. Okay, so because S3 and D6 are conducting, so this means that VAO voltage must be equal to 0. Okay, and since I have shown the direction of the current like this, so I must be less than 0. So this condition VAO equal to 0 and I less than 0, this is the correct condition, okay, at this point. So if in this converter, if I turn on S3 and D6, this is how the converter will behave. It will give a voltage of VAO equal to 0, and the current will flow into the converter. In a similar way, suppose I change the condition and I say that the current is flowing like this, okay, and I can turn on, I can give pulses to S2 and S3. Remember, so I take the next condition. Suppose I is now greater than 0. Under this condition, I get pulses to both S2 and S3. Okay, what will happen? The current will now flow from this to this, and through the IGBT, it will go like this. So for this orange color condition, I can say that I have given pulses to S2 and S3, but D5 and S2 will be conducting. And therefore, this immediately says that VAO will be still 0, but I will be greater than 0, greater than equal to 0. So which means the current will now go out of the converter into the grid. Okay, so this is how we can actually analyze the different behavior of the converter. Okay, next, let us take a small example. And here, this question, the pivot vector for realizing the reference vector VR using conventional specification interpretation is shown in 3 levels. So here the reference vector is at this position, right? So which pivot vector we will use? Okay. So in this case, we will think like this way, that this, for this reference vector, we have to take this hexagon, which I am going to draw now. This hexagon, okay, this is the proper hexagon on which the switching will happen. This is the hexagon, and in that hexagon, this is the pivot vector. Okay, so therefore you can recall what we have covered in the previous lectures, that the boundaries for the pivot vector, okay, the boundaries of the pivot vector are these lines. Okay, so when the reference vector is moving, right, the reference vector here VR is basically moving, right? So it is, yeah, it is tracking this. It is basically on this space vector diagram. And so if the pivot vector, if the reference vector is between 30° and 90°, okay, then this is the pivot vector. Okay, and so the hexagon on which the switching will happen is this one. So this is also shown by this diagram. So this is the hexagon that we will now use. If you take another example, suppose your reference vector is at this point. Okay, suppose at this point. Okay, so immediately you have to understand which pivot vector is now going to switch. So pivot vector, that's the starting and ending vector. So immediately you come here and see that I am now in this angle. So this will be my pivot vector. Okay, right? So this is my pivot vector, and the hexagon that will be used for switching is this hexagon, which I'm going to draw with the blue color now. Okay, so this is the hexagon which I am going to use. So here on this one, you can see that this is the hexagon that I'm going to use, right? So this way we understand that for any position of the reference vector, we can immediately find out which pivot vector will be used for realizing this reference vector. Pivot vector is basically the starting and ending vector that we are going to use in a switching cycle. Once we have identified the pivot vector, then we can immediately find out that which small hexagon we are going to use for switching purpose. Okay, so if this is, so this blue colored hexagon is the one which we will use. Inside the blue color, the actual space vectors that we will use for this one are these three space vectors, which I am now drawing with the red color. Okay, so V18 will be used as the pivot vector, and V10 and V11 will be used for the other T1, T2 duration. Okay, suppose you take the reference vector here in this. Okay, okay, so in this condition, then what will happen is the pivot vector still remains this one, but now you will switch on this one, and this one. Okay, and the calculation will happen. So remember that in a three-level space vector modulation or PWM, first you have to identify who is the pivot vector, and then you can identify, which is not needed, but you can identify which hexagon it is switching. And inside that two-level smaller hexagon, you can find out which are the three nearest space vectors that we need to switch. I have shown you a few examples. Also, you have to understand that this process of choosing the pivot vector, making the timing calculation, all these things are done automatic. Okay, you don't have to do this manually for any condition. Okay, it will be done automatically when you use the carrier-based SVPWM. Okay, the carrier-based SVPWM automatically does everything. It chooses the correct pivot vector. It will make the calculation on its own, and you don't have to worry anything about it. Only thing that you have to remember that we have to add two offsets, two proper offsets to the conventional space vector PWM, and we will get the whole thing automatically done inside the DSP. Okay, so this is the beauty of carrier-based SVPWM. Okay, so carrier-based SVPWM. You can see the other lecture also available in the YouTube. Right. Now, this is a very simple example just to elaborate this concept further. A three-level space vector diagram is shown in the figure. Okay, and the sampling time is 1000 microseconds. So this is TS. Okay, this is the TS, and VREF is 500. Here VREF is shown. So VREF is here exactly at this point. Okay, what will be the timing durations of V4, V5, and V15? Right? So we are, because it is at the boundary, so we may think that we can use these three vectors. Okay, so in this case, what will happen is, of course, as we understand that since this is at this position, V4 should not be used, okay, and V5 should not be used, right? Only then the reference vector will be exactly lying on the on this vector V15. Okay, so therefore we can say that V15 should be used for the entire time duration, and V4 and V5 should not be used at all, because only then we will be coming to this point. If you start using V4, what will happen? If you start increasing the time duration for V4, and so time duration of V4 is increased, and suppose time duration of V15 is decreased, then what will happen is that you will see that slowly the reference vector will start moving towards this direction. Okay, it will move, right? So if you start increasing V4 and decreasing V15, right? And similarly, if you start using V5 as well, then what will happen is the reference vector will start moving inside the triangle. Okay, so this is how the whole thing will work. This is how space vector PWM works. Okay, now the next topic that we will talk in details is the capacitor voltage balancing, which we have not touched upon so far. Okay, what is this capacitor voltage balancing? Now, there are two capacitors on the DC bus of the neutral point clamp converter. And this point here, this O point, so far we have assumed that this point is exactly at 0. Okay, so which means the two capacitors are exactly charged at the same voltage. Okay, but this is not true entirely. Okay, the midpoint voltage will be always not constant. It will fluctuate. Okay, when will it fluctuate? Of course, whenever we are accessing the midpoint. For example, we have seen in a previous example, the current I is suppose flowing through this way. Okay, right? The current is flowing through this way, and therefore we are basically accessing the midpoint O, and we are taking away some charge from the capacitors C1 and C2. Okay, so whenever we access the 0 voltage level of a neutral point clamp converter from any phase, then we are going to cause this O point to fluctuate. Okay. Um, so if you observe this O point voltage, what we see with respect to time, okay, if you see this VO, say we take VO with the negative of the DC bus, you will see that it has a voltage of VD by 2, but there will be an oscillation. So the average voltage here is VD by 2, but there is an oscillation that you will see, okay, VO with respect to the negative of the DC bus, right? Now, why is it important to study? The reason is that if there is a large fluctuation on the voltage, okay, remember these devices, all these devices, we have designed to be half of the DC link voltage, okay. Now, where we had assumed that these two capacitors are perfectly balanced and the voltage is exactly, the point O's voltage is exactly halfway between the positive and negative DC bus. If the point O voltage is fluctuating, going up and down, this assumption is no longer valid. Okay, so therefore the devices then have to be rated for more than VD by 2 voltage. So that is one problem. Okay, so we should actually ensure that this O point voltage is exactly midway. The other point that happens is we will have a poorer harmonic performance. Okay, and what happens here is that the output voltage, okay, so this A points voltage, we are expecting that VAO will be something like this, right? We are expecting VAO voltage to be something like this. However, if the O point voltage is fluctuating, what we will see is that these levels are no longer fixed. So if you zoom in into this one, you will see that it has this capacitor oscillation. So it will become like this. Okay, so it will have like this, the voltage, right? So there will be an oscillation or there will be this line here will not be stiff. Okay, it will have a it will include the low frequency oscillation, and therefore the harmonic performance will uh, get bad, okay, will get worse, and the THD of the current that we draw will become poorer. So that is why we need to ensure that this O points voltage is more or less like constant. Okay, now we will um, study a little bit more in how the actually the O point voltage fluctuates. Okay, so let us take a case in sector 1, okay, and where we are switching this switching combination plus 0 0, which means we are switching this one. Okay, and during this time, you can see if I assume that all the devices are perfect, all the IGBTs and everything is perfect, then during this plus 0 0, it means that A phase, right? A phase is connected to the plus VD by 2 and B and C phases are connected to the 0 point, right? So I have redrawn the circuit, omitting all the switches in between and just keeping the capacitors and the load currents, okay, which I have shown here. So the currents which are flowing are IA, IB, and IC in the three phases. But because I am using plus 0 0, so which means now B phase and C phase are both connected to the O point, right? Okay, now take the, so in this condition, therefore, IO, this current IO is nothing but IB plus IC, and assuming that we have a balanced system, it will be equal to minus IA. Okay, this current, suppose IA is greater than 0, then it means that the current is flowing like this, and I naught, this current is IA. Okay, this is flowing like this. I naught is equal to minus IA. The current comes from here and it is getting split into two parts, and then this current is flowing like this. So if IA is greater than 0, then what happens? Then C1 is discharging, right? Because the current will flow like this and will flow like this here. Okay, so which means that C1 is discharging, okay, and the midpoint voltage, so this is, so if I assume that the total DC bus voltage, the total DC bus voltage is constant, right? So what will happen is if C1 is discharging, then this midpoint voltage will go up. Okay, so therefore that's what I've said, V0 goes up here with respect to the negative of the DC rail, right? So we see that if we use this switching state of plus 0 0 and assuming that under this condition IA is greater than 0, at that instant the A phase current is greater than 0, then it will cause the uh, midpoint voltage to go up. Okay, now let us take the other condition. So instead of plus 0 0, suppose we take this switching state combination. Okay, and this is shown in this diagram here. So when you have 0 minus minus, then A phase is connected to 0, which I have shown here, that A phase is now connected to the 0 point, and this minus and minus, B phase and C phase, these are connected to the negative of the DC bus. Okay, so now what happens? I naught is equal to nothing but IA, okay, and which will be equal to minus of IB plus IC, right? So if now the same condition, if I naught IA is greater than 0, how will the current flow? It will come like this, and then it will divide like this and goes like this, right? And comes back and completes the path like this. So if IA is greater than 0, then what will happen is that then this capacitor C2 will be discharging, right? And therefore the midpoint voltage will go down, assuming that the total DC link here is constant. Okay, this is constant. So therefore we see that plus 0, 0 and 0 minus minus, these are complementary in terms of the capacitor voltage fluctuation. Okay, so if I assume, so if I can apply these two states, plus 0, 0 and 0 minus minus, for equal durations of time in a switching cycle, then I can make the midpoint voltage to be constant, okay, in a switching cycle, right? But you can do the same exercise by taking the any other small vector. Okay, all small vectors have actually two multiplicities, and these two multiplicities are complementary in terms of capacitor voltage fluctuation. Okay, it has complementary effect. Okay, all small vectors have complementary effect. You can do the same exercise once more with this condition, and you will find that for one condition, for one switching state, the midpoint voltage will increase, and for the other switching state, the midpoint voltage will decrease. Okay, now suppose you take the large vectors, okay, and say you can take any large vector, say plus minus minus, okay, or plus plus minus. These are large vector switching combination. So if you take plus minus minus and do the same exercise, plus minus minus means A phase is connected to the plus, so which has been connected to the VD by 2, and minus means the B and C phases are connected to this minus terminal. So what will happen? You can immediately observe that this O point is not accessed at all. Okay, so therefore the midpoint will not be accessed. And so hence the midpoint voltage will not fluctuate. So in general, we can say for all large vectors, the midpoint voltage does not fluctuate. Now let us take the medium vectors. Okay, take any combination, take any of the medium vectors. We take this plus 0 minus. Okay, of course you can see here that this uh, 0 is being accessed, right? So which means that therefore A phase, this is plus, and the B is 0 and C is minus, and therefore I naught, the midpoint current, is equal to the B phase current. Okay, and therefore it will cause the midpoint voltage to fluctuate. Okay, so this is true for all the 6 medium vectors. Okay, we have 6 medium vectors, and all of them will cause this. Remember that these medium voltage medium vectors do not have any multiplicity, right? So the medium vector, whatever happens, right, there are no complementary switching states to cancel the effect. Okay, and so capacitor voltage fluctuation due to the medium vectors has to be compensated by some other way. Okay, and that's what we will see, because there is nothing for the complementary effect. Okay, so this is like a summary. Okay, the zero vectors, of course, has no effect on the capacitor voltage. All the small vectors, if you take, they have multiplicities. The medium vectors are problematic because they change the midpoint voltage, and we must make some arrangement to cancel their effect, while the large vectors have no effect on the midpoint voltage. Okay, so there may be other causes of the midpoint voltage fluctuation also, and these are something like unbalanced operation or manufacturing non-idealities, or sometimes there is a sudden deviation of the capacitor voltage. Suppose there is a grid disturbance. Okay, so there is a grid disturbance here, and suddenly you are drawing more current from the capacitor midpoint, and it can have a sudden deviation of the capacitor voltage. So the midpoint voltage must be brought quickly inside the permissible limits in the shortest possible time. Okay. Now, uh, Um, let us analyze how much is the charge which is taken when there is a when we are accessing the midpoint voltage. Okay, so suppose we take a reference vector OA which is situated here. Okay, and for that we are going to use these switching states, as you can see, plus 0 0, plus 0 minus, plus minus minus, and 0 minus minus. These four will be used, right? Because of this. And we know from space vector PWM that these timing durations are something like this. Okay. Now, the charge, what we have seen, so we can draw the the uh, the switchings. So the way we have drawn these circuits. So if you draw this one, okay, just the way I have shown, you can find out that this I naught is equal to minus IA during this time, and it has been applied for T0 by 2 time period. Similarly, if you apply this plus 0 minus, the I naught value is IB, which has been applied now for T1 period. And there is no I naught taken when there is a large vector, and something like this. Okay. So if you add all of them, then the net charge Q, okay, will be this, and this will cancel each other. This one and this one here will cancel each other, assuming that in a small TS time period, the magnitude of IA remains more or less constant. If I assume that one, so then the net charge in one switching cycle TS is equal to this one, IB into T1, okay, which will cause the midpoint voltage to fluctuate. Okay. Now remember, now we have to compensate for that. Okay. So remember that uh, we cannot change the T1 and T2 time periods. Okay, because then it will if we change that one, then it will change the volt second balance. Okay, what we can do, what is possibility, is that these two time periods we will tweak a little bit. Okay, so the T0 is changed um, uh, unequally to balance the charge. Okay, and let us see how we do this one. So T0, that time period, is now made T0 by 2 plus delta T and T0 by 2 minus delta T. Okay, why did we do this? Because the total T0 by 2 time period should be maintained as before, right? Uh, but this comes from the volt second balance in a space vector PWM. So keeping that in mind, so let us see what we have done. So initially, if we have a normal switching, we have this plus 0 0 applied for T0 by 2 and 0 minus minus applied for T0 by 2. But in the modified switching, where we want to balance the capacitor voltages, we change this to T0 by 2 plus delta T and T0 by 2 minus delta T. Note that we have not changed T1 and T2. These two are kept as before, okay, same as before. We have not touched on that. So if you do like this modified time duration, what is the charge that is coming or going out of the midpoint? So this is I naught will be equal to minus IA, and now the modified time is T0 by 2 plus delta T. And here the modified timing is T0 by 2 minus delta T. So we can actually sum all this up, and this is shown here. The net charge flowing out of the midpoint, the total sum of the charge, if we add up all this, okay, the modified timing delta T, we can find out that if Q is to be made equal to 0, okay, we would like to make sure that the capacitor voltage after the switching cycle is coming back to its original value. Okay, so therefore the net charge must be equal to 0 after the TS time period. So if I then put this one, then I will know what is the value of delta T that needs to be introduced in the modified time duration. So we can know what are the values of this delta T that one must include or modify that T0 by 2 time period so as to make sure that Q equal to 0. This condition is satisfied. Okay, so this is one method of doing it. Okay, so if I can continuously calculate delta T, I can adjust it in the PWM technique. I will add this delta T. Okay, but although this is good, I mean, this is potentially a solution, but it has a drawback. What is the drawback? Is that the sensing of the currents will be required. Of course, you can see here in the expression of delta T, we have IB and IA, and the controller must know all the time the instantaneous values of IA, IB, and IC so as to calculate the value of delta T. Okay, this is one drawback. So we have to sense the current for that. The second drawback is how quickly, suppose there is a fluctuation in the capacitor midpoint voltage, and we want to quickly get the midpoint voltage back to the normal value. But at that point of time, okay, during that time, the instantaneous values of IB and ICR, IB and IA is low, or the ratio is low, okay, or it is not suitable. Okay, so then what will happen is we will require, okay, a lot of time for the capacitors to come back to the nominal voltage, because at that point we do not have that sufficient margin of delta T. Okay, another point which is also very important is that basically what we are doing here is, uh, remember this, we are changing the value of T0 by 2, keeping T1 and T2 to be constant. Okay, so but there are certain situations. So we have this T1 and we have T2 out of the TS time period. Okay, and the rest is the T0. T0 is the rest of TS, right? But now suppose we are in this, our reference vector is somewhere here. Okay, it is moving here. Now in this case, suppose we are here or we are close to the boundary. Okay, close to the boundary of the space vector. During this time, the T1 and T2 themselves are very large. Okay, and we do not have a good value of T0, right? So you can understand from this expression that T0, we are going to change T0 by 2 to T0 by 2 plus delta T. So we must have sufficient margin in the TS period so as to accommodate this change. But now, if T1 and T2 itself are very large fractions of TS time period, then we do not have the T0. So we have a very small fraction of T0 within which we want to tweak that one to T0 by 2 plus delta T, which may not be possible at all. Okay, we cannot add the correct value of delta T at all So when high modulation index, when this T1 and T2 are almost reaching their maximum value, T0 value itself is very small, and the tweaking on the T0 value to T0 by 2 plus delta T, that becomes very, very difficult. We do not have that margin in that TS time period so as to do this tweaking thing. So the midpoint voltage balancing becomes difficult at different levels of the modulation index. This is another drawback of the method. So uh, in order to rectify this one, there is something which is called as a virtual space vector uh, technique. Okay, what is this virtual space vector technique? Um, in this technique, what happens is there is something called as virtual space vectors. Okay, what is virtual space vector? In case of virtual space vector, we actually do not have, we make a new space vector. Okay, for example, here you can see this is a space vector which has been created virtually. Okay, this has been created virtually. What does virtually means? That if I switch this vector, and this vector, these are the three actual vectors. If I switch these three vectors for 1/3 duration of time, okay, then the effective vector I will get is this VZM1, which is called the virtual vector. Okay, if I switch this vector, and this vector, because this is an equilateral triangle, and this is, if I switch them 1/3, 1/3, 1/3, then I will create a virtual vector VZM1, which will be lying at the centroid of this triangle. Okay. Now, this vector VZM1 does not exist physically, because what exists physically and what is possible from the different switching combinations are these three vectors. Okay. This one, and this one. But now we are creating this virtual vector. Okay. So using this, actually, the midpoint voltage balancing is possible. This has been reported by a research group. I will later add this in the slides. Okay, I'll give a reference to this. There's a nice paper in IEEE. Stig, Professor Stig and his company and his research team. I'll add this one. So how does this virtual vector originate? Okay, how do we do this one? This is a very interesting concept. Okay, so we will use this virtual vector VZM1, but now we will change the whole concept of the space vectors. Okay, so now this sector, this is the 60-degree sector, which we are looking. And in this one, what is happening here is we have these vectors which are shown by the black dots. Okay. Now VZ0 is, of course, it remains like a 0, 0, 0. But how do I get VZS1? I get VZS1 by switching plus 0, 0 and 0 minus minus for half the duration of time. Okay. So I know that if I switch plus 0, 0, I get to VZS1. But now I'm switching plus 0, 0 for half the duration and 0 minus minus for another half of the duration. Okay. So effectively, I will come to this point. Correct? Now, the third vector, this is this one. Okay. The VZL1, of course, I will only switch plus minus minus for the entire duration. Similarly, VZL2, if you take this one, will be plus plus minus. Okay, this will be coming here. What about VZS2? This one. Okay, how do I switch this one? Again, half of plus plus 0 and 0 0 minus. Okay, if I switch both of them for half durations, then I will get to VZS2. Okay, so this is okay. These are okay. The thing that is interesting here is VZM1. How do I switch this vector VZM1? This is a virtual vector. I will switch it if I will switch it by switching 1/3 duration 0 minus minus. 0 minus minus is this one. Okay, then plus 0 minus this one for 1/3 duration, and plus plus 0, that is this one, for 1/3 duration. Okay, if I switch these three vectors for 1/3, 1/3, 1/3, I get to VZM1. Okay, so this is how this entire space vector diagram, okay, is now remodified. Okay, we are not going to use this vector alone. Okay, this vector we are not going to use, and now we are redistributing or redrawing the whole space vector diagram. Okay, and this is like showing it like this with different colors. So this 60-degree duration is now there are 5 regions. Okay, there are 5 regions, and these regions which are shown by this colored diagram, they are enclosed by new space vectors. These are Vz naught. So this region 1, so if you take region 1, it is enclosed by Vz0, Vzs1 and Vzs2. Okay, and then you have this region 2 which is here, and it is enclosed by Vzs1, Vzm1 and Vzs2. Similarly, region 3, region 4 and region 5. So suppose my reference vector is here, right? I will now switch this vector, and this vector. Okay, you notice that this thing is not specifically switched here. Okay, we are not going to use this one, but this switching state is part of VZM1. Okay, but we are now dividing this whole space vector diagram into 5 regions which are bounded by this which is bounded by this triangle which is shown by this violet color. Okay, that's what we are going to do. Okay, now one thing that we now say is that, okay, we have now remodified the space vector diagram and we are going to use this kind of a space vector, but all this we have done to make sure that the capacitor voltage is not fluctuating. Let us see what is the effect on the capacitor voltage. Okay, so suppose I choose this VZO, I have switched 0 0 0, and the effect on the midpoint voltage is 0. We know that. The second vector, suppose this is the first vector. The second vector VZS1, if I switch, how do I switch? I switch it half of plus 0 0 and 0 minus minus. And we have seen that if I have plus 0 0, the I naught will become minus IA. And if I switch 0 minus minus, the I naught is equal to plus IA. So the effect on the capacitor midpoint voltage is again 0. Okay, we have already seen that if I have this VZL1, it doesn't cause any capacitor midpoint voltage fluctuation. If we have VZL2, we do not have any problem. If we switch VZS2, if we switch this one, then we are going to use half and this switching state and this switching state. So therefore half of minus IC plus IC, right? Again, we find that the effect on the midpoint voltage is 0. Okay. Now about this one, VZM1, this is the most interesting vector. Okay, this is where the ingenuity, it's where this uh, um, uh, the beauty of this algorithm comes. Now suppose you have this VZM1. Okay, now in this VZM1, what am I going to switch? As I told you, we have defined the VZM1 like this way. Okay, we are going to use 1/3 and this switching state, this switching state, and this switching state. You can observe that there is a 0 coming on the A phase here, there's a 0 coming on the B phase here, and there's a 0 coming on the C phase here. So therefore, 1/3 of IA comes, then IB comes, and IC comes. Now, if that TS time period is sufficiently small, then we can say that if I use VZM1 for 1/3 like this way, then the effect on the midpoint voltage is equal to 0, right? So which means that if instead of the conventional space vectors, if I switch these 6 vectors, okay, these modified 6 vectors, right, VZ 0 to this one, all of them have no effect on the midpoint voltage, all of them. Okay, so which means now we do not have to worry about the midpoint voltage at all, because I will modify the space vector diagram, and in each sector we will have these vectors which we will switch rather than the conventional one, and we are sure that there is no effect on the midpoint voltage. Okay, so this is very nicely done through this algorithm. Okay, and this is again, we have seen that how the 6 vectors in one sector, we will switch it like this way. Okay, now let us see how we will actually switch. We have to remember that we are, suppose when we use VZM1, we are going to use this switching state, this switching state, and this switching state for getting VZM1. So we expect that the number of switching will increase, and that is true. Okay, because whenever we use VZM1, we are going to increase the number of switching. That is true. However, what we will see that this switching is only about 33% more. Okay, we'll see how much extra switching we are going to incur for this. Okay, so suppose we have a reference vector which is in region 2. So we have a reference vector which is here. And so we will be using these 3 vectors because this is in the blue region. And in that blue region, we have these 3 enclosing vectors. Now, if we were in this region 2 earlier, okay, if you see the dotted line, then what will be, if a conventional space vector PWM, how we will switch? So we can start with this plus 0, 0, that is this vector. We will go to the medium vector plus 0 minus. We will then go to 0, 0 minus. We will go to this vector, and then we will come back to 0 minus minus. Okay, this is the way we can actually switch, okay, for this reference vector. But now this is conventional space vector PWM. Now we are going to modify it in order to use VZM1. Okay, so in order to do that, the trick is that we will now, this VZS1, these are the vectors we are going to use for reference in sector 2. Okay, we are in now sector 2, and we are going to use these 3. And we have calculated that, okay, we need T1 duration, T0 duration, and T2 duration, okay, for this vector. Now, what is the first thing that we'll do is we will split T1 into T1 by 2 and T1 by 2, T0 to T0 by 3, T0 by 3, and T0 by 3, and T2 to T2 by 2 and T2 by 2, right? This is the first step that we will do. The next step is we will put how we define VZS1. Remember, we defined VZS1 as half of this and half of this. That's why we have split it into 2 parts. Okay, so for this, the combination used is 0 minus minus, and for this, the combination used is plus 0, 0. Similarly, for that VZM1, we have split the T0 part into 3 parts. For the first T0 by 3, we will use this combination. For the next T0 by 3, we will use this combination. For the last T0/3, we will use this combination. Okay, and then we will use VZS2, and this will be for this timing duration, and for this we will use this one and this one, right? Now comes the important part. Now we have to arrange. So we are going to use this row here. All the switching combinations we have to use, but we will now reshuffle this switching combination so as to make the number of transitions minimum. Okay, how do we do that? So in the TS time period, at first we put T1 by 2. Okay, so we use this one and put it here. Okay, this is the first one. Then we use this T0/3. Okay, right, and then we put it here. Then we take this T2/2 from here and put it here. Okay, then let me draw with a different color now. Then we take this +0 minus and put it here. Then we take another T1/2 and get it from here and put it here, right? And then we have this T0/3 coming here, and at last we have this which is coming here. Okay, so what have I done in this whole TS time period? What have I done is I have picked up this T1/2, T0/2, and T2/2 from this, not in this sequence, but in a sequence which I am going to which I am designing. Okay, so I have first given T1/2, then inserted the T0 period. Then I have introduced a T2/2, again a T0/3, again a T1, T0/3, and T2. Okay, in this sequence, the whole time period is adjusted. Why have I done this? What is the reason? Because I want to minimize the switching. Now you see what happens to the switching. So you see here, I started with 0 minus minus. Okay, then I went from this T1/2, I went to T0/3. I still have this 0 minus minus. So there is no change in the switching. Okay, so it's a good thing, right? Because I expect that when I use this kind of a modified space vector, I am going to incur more number of switching. In fact, it will be more, but how to minimize that extra switching? So then I go to T1/2 to T0/2. Now I am going to change from T0/2 to this, okay, VZM1 to VZS2. Okay, I'm going to now here from 0 minus minus, I'm going to 0 0 plus, sorry, 0 0 minus. So which means there is only this switching happening. Okay, this is the change. Okay, this is the change that is happening. So there is one change. When I go from T2/2 to again this, so you can now see the benefit of arranging these switching states. I have done it manually. So you can see now 0 0 minus 2, it goes to this one, plus 0 minus. Again, only a phase changes. So therefore, there is only one change. Similarly, when I go from here to here, there is one change, plus 0 minus 2 plus 0 0. And from here to here, if I go, then this is also there. There is only one change. And again, at the end, there is no change. Okay, so you can now understand why I arranged the space, the switching or the space vector in this particular fashion, because I found that I have no change here and no change here. That is good thing. But in between, I have 1, 2, 3, 4, 4 switching transitions. Okay, in conventional space vector PWM, in TS time period, I have 3 switching transitions. Okay, but in this case, now we have 4 switching transitions. Okay, so therefore, we can say that for this 4 transition, in conventional space vector PWM, we have 3 transition. So we have 33% more switching. Okay, with this technique. But what is the plus point of this technique? is that we have now been able to completely get rid of the problem of capacitor midpoint fluctuation or the DC link midpoint fluctuation, capacitor voltage fluctuation, because we are going to use space vectors in such a way that all these space vectors have zero effect or no effect on the capacitor voltage fluctuation. So this is the advantage of this technique. Okay, it has been also this thing of arranging the space vectors, I have done it manually here, but it can be also done with a carrier based approach. This has also been reported. So you don't have to worry how to arrange, when to place which vectors here and there. Entire thing can be arranged through a carrier. And so then you don't have to worry anything at all. You put that modulating waveform with the carrier and it will automatically be done. Okay, so there are papers on that also. Okay, now of course, now we end that topic and we say that we have seen that this is a two-level converter, and then you have three-level. When you use multi-level, so 5 levels or more and more levels, the space vectors in the space vector diagram become denser, and so the instantaneous error is reduced, and we require less amount of filters, and the THD gets improved. Okay, so this is a different topic altogether, higher level converters, for which the YouTube lecture you can refer to. Now, there is one thing which I want to cover is what is known as the T-type NPC, which is called TNPC. Okay, as I told you, while we were uh, de deriving the circuit of the NPC, we said that we can actually use this circuit. Okay, in fact, the original inventor of this NPC, they were aware of this kind of a circuit. Okay, however, at that point, about 30 or 40 years back, at that point, the availability of power devices were not like that. And so we have gone to the neutral point clamped NPC, neutral point clamped converter. But as power devices become more and more powerful, when the voltages are higher and higher, and we are getting it in cheap also cost-wise, and silicon carbide has also come. So we can actually now go back and see that what is this T-type NPC and what is their advantage. Okay, this converter is now commercially being used in many applications. Okay, and this we will see in the next part. We will see that this is nothing but very closely related to the VNR rectifier. Okay, we'll see this one. Okay, basically it's the same thing. Okay, it's a T-type NPC, but somewhat like the IGBTs have been removed and diodes have been put there. Okay, so the T-type NPC, in this one, what happens is that in the NPC, we had these clamping diodes during the zero state. Okay, we had this one, and that is actually going to cause more losses. Okay, um, and even in the plus and minus states, you can remember in the plus or minus state, what happened? There were two switches conducting. Okay, but in this topology, you can see that there are only one switches. The operation is very simple actually. The operation is that if you want to have VD by 2, you just turn on S1. Okay, you just turn on S1 and the current will flow. And if you want to get 0, you actually turn on both S3 and S4. Okay, S3 and yeah. So if the current direction is greater than 0, okay, so if the current is greater than 0, then S3 and D4 will conduct. Okay, and suppose you want to get the negative voltage, you just turn on S2, give the gate pulse to S2, and D2 will start to conduct. Okay, this is the condition when I0 is greater than 0. And if I0 is less than 0, okay, like if the I0 is less than 0, then what happens is if if you want VD by 2 voltage, then this will flow. The diode D1 will conduct. If you want 0 voltage, you turn on S3 and S4. And in this case, because I0 is less than 0, so S4 and D3 will conduct. And if you want to get minus voltage, you just give this negative, this one. Okay, it is pretty simple, easy to understand. But one thing that is important to note here is that what is the rating of the devices, right? As you can understand that suppose this switch is conducting, then when this switch is blocking the full voltage, how much it is blocking? So this minus point then comes here. So this is the minus point and this plus point is here. So this means this switch must be rated for the full DC link voltage. Okay. Similarly, in a very similar argument, I can always say that this voltage is, this device also must be rated for the full DC link voltage. What about these two switches? You can understand that they will be rated for half the DC link. Why? Because you see, okay, this is a 4-quadrant switch. Okay, this is important. Why did I use this kind of a switch? So if you go back, this is a 4-quadrant switch, right? So let me go back and see why it is needed. Okay, so just we will remove this one and see why this switch is something like this. How did it come? Okay, now suppose when you connect this switch to this point here, what you see is that this plus voltage comes here, okay, and the current will flow. Now take the other condition. So therefore what happens is this this switch has a plus here and the 0 here, right? So it has to block the voltage like this way. Now you take the other condition where this switch is conducting. Then this minus comes here and the minus is here and the 0 is still here. So then this switch here, okay, this S3 and S4 combination has a minus here. Okay, so which means that the switch has to block. So if I represent this switch as this way, so sometimes this side is plus and sometimes this side is minus. So which means it has to block a voltage which is bidirectional. Of course, the current can flow both ways. It can flow through this one or it can, because it's an AC current, okay, AC. This current here is AC. So therefore, it can flow both in and out. So therefore, this switch, the current can flow in both the directions and it has to block both positive and negative voltages. So therefore, we say that suppose this I put the I and this is the blocking voltage, I will say that this is a 4-quadrant switch. Okay, so that is why I have chosen this switch as this one. Okay, this is one type of 4-quadrant switch. Other types of 4-quadrant switches are also available and you will see it in Vienna rectifier. Okay, other types of 4-quadrant switches. But T-type NPC, what is the advantage that we get? This converter is basically decreasing the power circuit device count. Okay, so in conventional NPC, there are 4 switches, 4 antiparallel diodes and 2 clamping diodes. But here you do not have so many. You have 8 switches. So you have been able to remove those extra switches which are needed in the plus and minus. And therefore, actually it increases the converter efficiency. In particular, during the plus and minus states, you can see only one device is conducting. Okay, but that device has to be rated for the full DC link voltage, unlike neutral point clamp converter where all the devices were rated for half the DC link. So this is possible. This has become attractive because now we have very powerful switches at low cost, which was not available 40 years back. So now we have low cost switches, good rating. So this TNPC, we actually prefer it more, because then the size of the converter losses will go down and the size of the converter will go down. The heat sink requirement goes down. And so we are in an advantageous situation. So therefore, TNPC is one of the important three-level converters, which we will in future, many people are expected to use it. So let us conclude that we have studied this NPC converter, we have studied the topology, we have studied the PWM technique, and also the capacitor midpoint voltage balancing technique. And it can be used as a front-end converter for interfacing with the grid. Generally, a neutral point clamp converter is a very popular converter, and it is used at higher power levels, okay, hundreds of kilowatt and medium voltage, where two-level voltage source converters are not so much used. Okay, it's better to use a neutral point clamp converter. It is used throughout the world for different applications. Okay, with this, we conclude the lecture.